So it's a great pleasure to introduce Matthew Pickering. When I was a medical student, compliment was a subject that completely passed me by. I thought it was just really for really clever people, and some of the people who taught it were really clever, but they didn't make it easy to understand. Now I've got a bit older, I realize that compliment is not so difficult, but what Matthew is an expert, a world expert on compliment, what he has a unique skill at doing is making compliment easy for people to understand. So I'm delighted he's come to speak to us about what is compliment and what does it do. Thanks, Matthew.
So thank you very much. It's a real pleasure to be here. Can I just go off-piste like Mark did? And for the non-experts in the audience, just put your hand up if you understand what compliment is. Okay, so we have one. So my son, who I practiced this talk on, said, you ought to do this at the end as well, and that'll tell you whether or not you've been successful. So like Sally did with hemolytic uremic syndrome, I think it's good to go for a definition. So let's start with a definition of compliment. And this is the Oxford Dictionary definition of compliment. And like all dictionaries, it starts off with an origin of the word. You can see it comes from Latin, meaning to fill up. But of course, now we define it as a thing that contributes extra features to something else in such a way as to improve or emphasize its quality. And here's the example they give. Okay, local ales provide the perfect complement to fine food. And of course, that's not what we're here to discuss today, unfortunately. But they go on to give the scientific definition. So here we are. A group of proteins present in blood, plasma, and tissue fluid which combine with an antigen-antibody complex to bring about the lysis of foreign cells. So that's completely clear. Okay? Well, you couldn't get really a more boring and dry definition of complement than that, and we can do a lot better. And what I like to do when I'm talking about medical systems like this is to go back to the very beginning and ask, where did it all start? And it starts here in 1895. This is Jules Bordet. And Jules Bordet was studying how blood destroys pathogens. Now, a pathogen is something like a bacteria, for example, that causes disease. And Bordet was working at a time well before the development of antibiotics, when deaths from infection were very, very common. And what Bordet noticed was that there were two components in blood that were important to destroy bacteria. Okay? The first is what we now call antibodies. Okay? And antibodies, which I've shown schematically in the slide in front of you, are proteins that target specific structures, things on foreign cells. Okay? The second component was a mystery to Bordet, but he knew that it enhanced the ability of these antibodies to kill bacteria, and that it was damaged when you heated blood up. It was heat sensitive. And he called this alexin, which comes from the Greek, you'll know this. I didn't know this, I looked it up, to ward off. Okay? Now, Bordet was a very talented researcher. He made huge contributions to understanding infection, and he went on to get a Nobel Prize. But alexin didn't really catch on. And in 1899, Paul Ehrlich coined the term complement, because Ehrlich wanted to emphasize that complement, whatever this was in blood, enhanced the quality of the blood to kill bacteria. And you can see here the first time this word was ever used in 1899. Now, Ehrlich was a research superstar, and he's famous in medicine for many, many things, but you may recognize the term magic bullet. Okay, this was the subject of a Hollywood film based on Ehrlich's search to find a chemical that would specifically kill pathogens without damaging your own cells. Okay, and he achieved this after many, many years. He found a chemical that would kill the organisms that cause syphilis. Okay? And we'll come back to that concept of magic bullet at the end of the talk. Now, like Bordet, he went on to win a Nobel Prize. He was a very deep thinker, and he knew that whatever this component was, complement was, it must interact in some way with antibody. And this is a drawing from 1900, where he is telling us an important clue. The antibodies interact in some way with complement. And from his subsequent writing, it's quite clear that he understood that this was a very complicated system. And it would not have been a surprise to him that it would take us many, many decades to unravel the complexities of complement. Okay? So we've got lunch at 12:30, so how are we going to get from 1895 to 2011? Well, what we're going to do is we're going to talk take a journey using three narratives. And firstly, we're going to look at how the characterization of complement. Secondly, we're going to look at complement disease, and of course I'll talk about HUS and the influence of complement there. And finally, we're going to talk about the advent of drugs that doctors can now use in the clinic to control complement when things go wrong. So here's a definition of complement, which I think is much more meaningful. It's a network of proteins. There are many of these proteins. The number's not important. They interact, and the main purpose of complement is to fight pathogens, so stop us getting infection. Now, in the presence of pathogens, complement will unleash a series of actions which culminate with killing the pathogen, okay? And I refer to this as the firepower. You can see it schematically there. And complement's very good at this, and it has several ways of doing it. It can kill the pathogen directly, okay? It can label the pathogen for destruction by cells in the body. And also, very importantly, if you're fighting a war, it can call for help, okay? Alert the body that something is wrong where the pathogen is sited. So how does it kill pathogens? Well, you know, you may be squeamish here. It assembles a group of proteins, and this group of proteins we use, the jargon is a complex, which has the ability to punch holes in the surfaces of these bacteria, for example. And what happens then is that the bacteria or pathogen has a very undignified demise. It can literally explode. Okay? This is a very powerful system of getting rid of pathogens. And we can see here on the right a very strong microscopic image of these holes on the surface of a pathogen. Now, we call the surfaces of a pathogen a membrane, so the jargon here, which you don't need to remember, is that this complex is called the membrane attack complex, but it's quite appropriately named. You can see why researchers coined that term. Complement can also, as I said earlier, coat the membrane of bacteria with proteins. And these proteins send signals to cells in the body that this organism needs to be destroyed. It's eat me signals, okay? And that will alert cells that I've shown on the right there that eat pathogens to come along and clear that bug. And finally, it doesn't get any better for the pathogen, if you like. Just to make sure that things are safely removed, complement sends out signals that call in other cells to the vicinity, okay? The cavalry is coming, okay? So if complement can't kill the pathogen directly, cells will come in which will do the job. So it's a very, very important and potent process, multifaceted, in protecting us against infection. And this is very necessary because pathogens are very cunning and devious, and throughout evolution, nature has taught us that there's not much room for maneuver when it comes to fighting infection. So let's look at the detail of this network of proteins. Well, we know that there is some order in which the complement system is turned on. It's organized into 3 pathways, the classical, lectin, and alternative pathway that you can see in front of you. And this all culminates in the activation of this firepower. So whichever pathway is turned on, they can all activate the firepower. And there are many different names and proteins, and we don't need to go into the details, but let me introduce you to the star players. We have friends from Spain here. These would be the Lionel Messis, the Iniestas of the complement system, okay? Why do I say that? It's because from these proteins, this is where the firepower, the components of the firepower arise, okay? C3 and C5. Now, this is self-evident. We have this very strong system that's able to fight pathogens. We obviously don't want to fight our own cells. There must be some way in which we control this. Okay? Complement has to be able to distinguish between pathogens, one of them, okay, and our own cells, one of us. And this is very, very important. So this was a topic that researchers have looked into in detail over many, many decades. And we now know quite a lot about what turns these pathways on. So what you can see in front of you here is what turns on the classical and lectin pathways. Okay? So the classical pathway is switched on by antibodies. Remember, we saw the schematic at the beginning that bind to the surface of pathogens. What you can see here is antibodies binding to bacteria. And that event, in the jargon we call that an immune complex. And that is a signal to the classical pathway to turn on and activate the firepower. And that doesn't happen on our own cells generally. So again, the classical pathway will not damage self. The lectin pathway recognizes specific sugars on the surface of bacteria. Okay? We have sugars on our own cells, but fortunately they're not the same as the sugars on the bacterial cells. So again, the lectin pathway does not normally injure our own cells. But here's a special exception. This is the alternative pathway. Okay? And the alternative pathway is special because, unlike the other two pathways, it's always switched on. You can think of this pathway as essentially attacking everything. Okay? That's very appropriate. It'll attack any bacterial substance, for example, but it's inappropriate in its indiscriminate activity, unless it is controlled, will start to attack our own cells. Okay? So we have to understand why that doesn't happen. And this leads to this concept, okay, which was again a subject of intense research. What switches complement off? And our cells are not normally affected by this indiscriminate activity of the alternative pathway because we have evolved to have switches on the surface of our cells that turn off the complement firepower, okay? As I've shown here. So this prevents any damage to our cells. Bacteria don't have these switches, so they can't prevent this from happening. And in addition, the alternative pathway also has its own regulators, or off switches, which turn the activity down to a very low level. And we've heard already one of the key switches in this pathway, which is factor H. Now, these, like a lot of the protein names of complement, if you get into the detail, it becomes confusing because the names are very, very strange, and the names of these regulators are strange. They're familiar to you now from obviously experiences with HUS, but these cause confusion amongst doctors and medical students as well, and add to the complexity that Tim referred to at the beginning. So we have factor H and factor I. We have names like CD46, okay? Very confusing, but the detail's not important. Just remember that these are turning off this pathway and protecting our own cells appropriately from this indiscriminate activity of the alternative pathway. To add even more confusion, some of these regulators have two names, and this will cause problems if you look on internet searches and you start trying to get into more detail, okay? This adds some confusion. But again, it doesn't matter. The principle is that these are very important in down-regulating the firepower of complement and its effect on our own cells. So that tells us really the key aspects of characterizing complement that we have to understand if we're then going to make any sense of what happens when we look at complement and disease. And I like to split up the next theme, complement and disease, into two aspects and talk about them briefly. The first is, if you can't turn on one of those pathways, something's happened, you're missing a protein, you're born missing a protein in, for instance, the classical pathway, you can't turn on the pathway. Then you have, if you like, too little complement. You have a pathway deficiency. We can't activate a complement sufficiently. And you might suspect that that will cause problems in defending yourself against infections, and you would be correct, and we'll see that in a moment. And then we look about the opposite situation, where there's a problem in switching off the system. Okay? You're born with a problem in one of the off switches. So you can't regulate complement sufficiently. And if you like, you've got too much complement activation. And of course, atypical HUS falls into this category, as we'll see shortly. So we understood a huge amount about complement biology from understanding what happens in infection, from doing experiments in laboratory, but very, very importantly, from studying what happens to individuals who are born with problems in the complement system. For example, missing activation proteins. So in the 1970s, so you can see 75 years after Bourdet described complement, we identified the first individuals in the world who had been born without any of those star players of the complement system. They're missing C3 and some are missing C5. So what happened in this situation? Well, of course, if you don't have C3 or you don't have C5, the firepower is greatly reduced. And these individuals are very susceptible to infections. And it's very important for us to remember what happens to these individuals because it has implications when we start to switch complement off for treatments. And one of the infections, clearly, that was described was meningitis. Okay? Now, fortunately, what tended to happen in these individuals was that as we move from children to adulthood, our antibodies become more sophisticated and numerous. Okay, so the outlook is relatively good. So complement plays less of a role in fighting infection as we age. So these individuals tended to have lots of problems with infection when they were children, but as they became older, the number of infections reduced. So let's go back now to the second type of complement problem, too much activation, a problem with these off switches. And we're talking here, of course, about atypical hemolytic uremic syndrome. And I've introduced the 1998 here, and you've heard from Sally the seminal paper by Professor Tim and Judith Goodship, which really started the link between complement and atypical HUS in 1998. But let's look at conceptually what is happening here. So a long time ago, it was discovered that there is an illness in which you can develop red blood cells which don't have the appropriate off switches on them. Okay? They circulate in the absence of these off switches, and these become very sensitive to damage by the indiscriminate activity of the alternative pathway. And you end up with these cells exploding in the same way that I said can happen to pathogens, which of course is appropriate. You don't want infection. But of course you don't want this happening. You don't want your own cells, red blood cells, exploding in the circulation. But what this was telling us was the importance of these off switches. And this condition, and some of you may know about this, or if you've searched on the internet about complement, it often comes up, is given a very fearsome name, which is paroxysmal nocturnal hemoglobinuria. Doctors like to put things in very complicated terminology, okay? But really, we're not saying anything clever at all. Paroxysms means episodes, nocturnals, night, hemoglobinuria, blood in the urine. So we're translating it, but we now understand exactly what's going on. And of course, you can see what we should do about treating this condition is we should switch off the complement activation, and then we would predict that these red cells won't explode and the patients would feel a lot better. Now, what's happening in atypical hemolytic uremic syndrome? Well, you've heard of some of the key regulators, off switches that have been associated with this syndrome. And what we're getting here again is the concept is that there's poor control of this alternative pathway and protection of cells from complement. And we know that factor H, we've heard about that, factor I, and CD46, these are important off switches, are all associated with this syndrome. We also know that the alternative pathway can actually have proteins which become superactive. Okay, so even if these switches are working normally, there are some individuals who have a superactive alternative pathway, and they can also get atypical HUS. And all of this is tied together by an increased activity of this pathway, a defect in the off switches or a defect making the activation enhanced. And of course, this damages the kidney cells, the lining of the blood vessels in the kidney cells. And I've written there renal endothelium. And this is the atypical hemolytic uremic syndrome. And this summarizes really a lot of work, a decade of very impressive work going from 1998 to the present, understanding the associations between complement and this condition. So we now come to our final theme, and that is drugs that control complement activation that we can use in the clinic to treat complement when things go wrong. And of course, let's go back to the schematic where we look at the star players, the C3 and C5, that unleash the firepower that is appropriate in the presence of a pathogen, but not appropriate on our own kidney cells or on our blood cells. And of course, these are C3 and C5. Eculizumab, and a lot of you would have heard of that, is a drug that blocks C5. And it's very, very good at reducing the firepower of complement. And I hope you can begin to see why now, because if we take away C5, we take away 2 of the components of the firepower. Okay? And this has been shown and has been used since 2007 in individuals with that red cell disorder to stop red cells from getting damaged by complement successfully. And you can see here on the right a picture of eculizumab, it's called Soliris, and you can see the words, the first medication specifically indicated to treat individuals with PNH. okay, because this is a logical treatment that has been based on understanding what was going wrong. Okay? And of course, that's 2007, the use of eculizumab for PNH. And what we're going to hear about later on is the use of this agent in 2011 for the treatment of HUS. Okay. So I finish on a very optimistic note. I think that over the last 100 years, we have unraveled a lot of the mysteries of complement, and Jules Bordet and Paul Ehrlich would be very impressed with our progress. However, if you recall the magic bullet concept, Ehrlich's his research strive to try and find chemicals that would specifically kill pathogens that caused infection without damage in host cells. Okay, and you remember, he was successful. He achieved this magic bullet to kill organisms that cause syphilis. I think he would find it fascinating that we've used much the same approach, okay, to devise an agent that specifically targets one of the key components of the complement firepower. There are many more of these agents in development, and the future for individuals with atypical HUS is very, very bright. And I'll finish on that optimistic note. Thank you for your attention.
Thanks very much, Matthew. Were you going to ask your question about who understood it now?
Ah, yes. So hands up if you feel that you understand complement now. Let's take a picture.
Does anybody have a question they want to ask Matthew?
Yes, please.
Genetic abnormality that causes HUS, what triggers it off? Because my symptoms developed in my 50s. Yeah. But I must have been born with it.
Yes. That's an excellent question. And what we know is that there's a very fine balance in the regulation of complement, and almost certainly what can happen. And we think, for example, in infection episodes, the kidney can become more susceptible to this imbalance. So this is not a full-blown situation that develops as soon as you're born, clearly. Okay, but is really triggered by other events. And there's probably a very interesting interaction between infection, episodes of infection, and the development of the syndrome. And you can see that that may not surprise you because of the close link between complement and its fighting infection, okay, and what we know about complement damaging the kidney lining in the syndrome.
Does that mean it would have come by way of a virus?
Potentially that is possible, but it's much more likely that bacterial infections can cause what we call inflammation in the body. You can clear the bacterial infection, but you become, if you like, just a bit more primed to the sensitive effects of complement. So we know that from a lot of the studies that have described courses of HUS, that many of them appear to be preceded by episodes of infection or illness. And some of those, it's very hard to know exactly what causes that. And you're right, it could be a virus, it could be a bacteria. In most cases, we just don't know.
Can I just say that when Jana became ill in Switzerland, I had a cousin whose son in his 20s became ill. And as Dr. Goodship will know, that they did a study into our family because we all went and had a blood test to see if we had this particular gene. And it was identified in our family. And I think what was interesting was the amount in the family that actually had the gene. I've got 4 brothers as well, and out of the 5 of us, there were 4 that had the gene, the defective gene. And with our own family, we had 2 children before the 2 we lost. We had 2 boys and we had Becky. And in our family, there were again 4 out of the 5 that had the gene. So we aren't all affected, and what triggers it off, I think, is just absolutely amazing. Yeah. There's no explaining. And if I tell you that my father had the gene, his blood was taken by Dr. Goodship in the 90s, and he had the gene. He lived to be 94. And the previous generation, if you looked at that, there were 10 born in that family. And if you looked at that, there were possibly 2 that died. One was, when he died, had no red blood cells in his body, and the other one had Bright's disease, which was a kidney disease. And of that family, I think it was either 5 or 6 lived to be in their 90s. So, you know, they probably had the gene as well. So, but they carried it all their lives, and nothing ever triggered it off. So it's incredible, really.
Yeah. Yeah.
Hi. Has any work been done to understand exactly how CFH behaves when it's mutated, and how each mutation in each SCR actually manifests itself?
There's a huge amount that's been done looking at the effects of these mutations in HUS, and specifically trying to understand we would call it, I'll use a jargon here, we would call it the molecular pathogenesis, what precisely is going on. And what we know is that these mutations in HUS interfere with the ability of factor H to bind to surfaces like the kidney, okay? And factor H can act as an off trigger, both in blood, keeping the alternative pathway low, and also it can act on the surface of the kidney cells as an off trigger. And that action on the surface of the kidney cells is impaired by the mutations that cause HUS.
Sorry, just one more on that point then. The factor H that's free-flowing in products like Octaplas, does that act in the same way as a person's own factor H? In other words, does it still recognize self cells?
The answer is yes. Octaplas contains most complement proteins all in their active state. So we've used this not only, it's not only been used, if you like, to give back functional factor H, but we've also used this to replace proteins that are deficient in these rare individuals, C3, C5 deficient individuals, for example. So yes, Octaplas contains functional complement system.
At the back, I'd like to thank Matthew again. Thank you very much, Matthew.